So next we will move to Lorenzo. Dr. Lorenzo Jamone is a senior lecturer at Queen Mary University of London. He is an expert in cognitive robotics, and particularly on dexterous manipulation, object affordances, visual haptic perception, and exploration. And welcome, Lorenzo. Lorenzo, are you here? Can you share your screen, please?
Yeah. Hi, everyone. Right. So, okay. So, can you confirm you see my screen? But
yeah, I can see the screen. Yeah.
Do you see just the screen, or you see also the images of the people?
Yeah, I can see these logos. Very nice logos.
Okay, you only see the slides, right?
Yeah.
Okay, fantastic. Okay, well, thanks a lot for the introduction, Sean, and for the invitation, and and for organizing the workshop in the first place. And thanks everybody for attending. My name is Lorenzo Jamone. I'm a senior lecturer in robotics at the Queen Mary University of London. And the title of my talk today is Magnetic-Based Soft Tactile Sensors for Robotic Manipulation. A little bit of introduction first. So, okay, let me minimize this. Okay, so a little bit of introduction, I was saying. So I work at Queen Mary University of London. This is one of the Russell Group universities in the UK, meaning the best 25 universities for the quality of our teaching and research. We are ranked 100 in the world, and we are quite research-based. So we're doing even better in research than in teaching. We are ranked 9 in the UK. We are quite proud to be very diverse and inclusive. And in fact, half of our students are international, and about 70% are coming from Black, Asian, and other ethnic minorities, which I think it's very interesting. And that mixed with the other 30%, which is white like me, it makes a very diverse and nice environment, I believe. And at Queen Mary, I am part of ARC, which is a robotics center that was established now about 5 years ago by Professor Kaspar Althofer, who's also among the organizers of this workshop and is here today. And we tackle different aspects of robotics. We make bodies of robots, but also their brains, and we apply them to several applications from industry to nuclear decommissioning, assistive robots, etc. As for myself, specifically, I lead a team that is called CRISP, Cognitive Robotics and Intelligent Systems for the People. And we have this twofold objective, which is the objective of cognitive robotics, I would say, to create smart robots, taking some inspiration from biological systems and from humans, and at the same time trying to understand more about human intelligence. And I have to be honest that we focus more on the first objective, which is to create smart robots, but I personally find the other objective equally interesting and important. And we have a number of projects, and especially what we focus on is the intelligence of our hands. So the extraordinary abilities that we have as humans to grasp and manipulate objects, to explore the environment and gather information by physically interacting with the environment, and also to use the hands to improve our perception and improve our interpersonal communication. And I will just mention a couple of projects that we have funded by the UK, by the EPSRC Council, and in collaboration with a few companies. So a big project in which we are involved is the NCNR. This is National Center for Nuclear Robotics. This is a very large project with several universities and companies involved. And in this project, as Queen Mary as a whole, we deal with a number of activities. And specifically related to the topics of this workshop are our work on tactile sensing, grasping, manipulation, which is also the part in which I personally mostly involved. And a smaller project that I am leading is called Mantri, and it's about learning dexterous manipulation from human demonstrations. And here we collaborate with Ocado, which is an online supermarket in the UK. By online supermarket, I mean that you can order food only online. They don't have physical stores, but they have, of course, physical warehouses where they prepare the orders for people. And most of the jobs there are done manually at the moment. They would like to use robots more and more. And this is where we come in together with their own research division, of course. And here the idea is to have humans demonstrating through teleoperation. And in fact, we have a simple bidirectional teleoperation system that is actually very affordable, but it provides also the tactile feedback back to the user, which I think is quite important. And these are the kind of tasks we are interested in, picking object in boxes. And especially we are interested in trying to understand what are the manual strategies that humans employ to pick objects when it's not trivial. For example, if you have multiple objects, you may want first to declutter the scene by moving your fingers around and then maybe pick one object. Or for example, maybe you want to first pick the object only with 2 fingers and then lift it and then enclose it with the rest of the fingers to make the transportation phase more robust, this kind of thing. So we hope to extract some of these motion synergies and these strategies from human demonstration. And then, of course, we want to realize them in the robot. And when we do that, this is an example in which we actually provide the demonstration by kinesthetic teaching. When we provide the motion, then we want the robot to reproduce it robustly. And for this, actually, tactile feedback or force feedback is very important. You see here an example of using or not using tactile feedback. And we use a form of compliant control. And what we're very interested here is generalization. So after we teach one action, we would like the robot to generalize. For example, do the same action with a different object, like a smaller or a larger object, or performing the same movement, but with a different amount of motion. And here, well, just briefly, I'd like to mention how we do it. And this is partly similar to some of the things Aude Bilar presented in her talk. However, I think one difference here is that we try to use real-time learning for adapting to a specific object, because we think this approach might possibly favor generalization when we do not necessarily train and then reproduce actions on the same object, but we would like to use a larger variety of objects. And specifically what we are interested in, and this is things we are currently investigating, is to have a process of tactile exploration in which we try to determine or estimating what is the friction cone and the friction properties of the object and the interaction. And so that we can then use in order to improve the grasp and to make it more robust and improve the general stability of the movement. And in terms of our, so mostly related to the NCNR project and in general also for other application, we then try to combine computer vision and tactile sensing in order to realize autonomous grasping. And here basically we want to use vision to get initial information on where the objects are and how to position the gripper in this case, or the hand of the robot. And then we use tactile sensing to improve stability, to detect slip and to react to that. But in some situation also to understand something more about the object. For example, to do some kind of tactile inspection to understand some physical properties of the object. I think tactile sensing can be interesting in this sense as well. And in fact, I think in the talk today, I will mainly present a type of tactile sensing that we are using that is based on magnetic technology. And I would like to present a couple of applications, putting forward this idea that in fact tactile is important to handle challenging objects, for example, delicate objects when you want to regulate the force precisely, but also to obtain additional information about the object while you are manipulating them. That ideally could be, I think, an interesting goal. Okay, so with this, I will start to introduce the technology we use for tactile sensing. And of course, we know that there are several technologies out there, and we already seen several examples in the previous talks. For example, many of them based on optical sensing. In our case, we use magnetic, and I would like to point out a few characteristics of using magnetics for tactile sensing that I think they make it particularly interesting. I won't say better than other technology. I don't think there is a technology that is intrinsically better than others. I think it depends a bit on the application. But some aspects that I think are interesting in the case of magnetics are that we can achieve high sensitivity and high signal-to-noise ratio of our measurements, a fast response, and then it's relatively easy to produce this sensor and to integrate them and also to miniaturize them. And I think what this brings is that we can measure contact forces that are very small. We can do it robustly with low level of noise, and we can do it quickly, we can do it fast. And because we can miniaturize the sensor, we can put many of them. I think these are the interesting aspects, which of course are shared by other technologies, but I think in the case of magnetic, they are particularly relevant. And we take mild inspiration from humans in terms of what kind of sensors we make. And as you know, in the human skin, we have several tactile receptors. This is just a couple of examples. We have Merkel's disc, and we have hair follicle receptors. And we took inspiration from them to create two different families of sensors based on similar ideas. And I will tell you now a bit more how do they work. So for this type of sensor, the idea is that we have a magnet which is immersed in a soft material, and then we have a magnetic sensor below. So the magnetic sensor will measure the magnetic field generated by the magnet. When there is a contact between the sensor and the environment, the soft material is deformed. The magnet moves with respect to the sensor, and so the magnetic field that is measured by the sensor will change. And this can give us an indirect measure of the applied force. If we use a Hall-effect sensor that can measure the magnetic field in 3 dimensions, then it means that we can get an indirect measure of both the normal force and the shear forces in both directions. So we can have effectively a 3D sensor, a 3D force sensor. And in fact, we have made sensors based on this technology that are, as I said, very relatively easy to make. And here you can see in the video, the sensing from the index finger. Now it's touching the robot, and you have a normal component of the force that you see this relatively light force being detected. And then when we lift the object, you will see also a shear component of the force appearing. And you can see that the forces that we measure are low. And in fact, this is a very delicate plastic cup. And you see some ideas of the construction process on the left. So basically you have this small magnetic sensor, you put it on the finger of the robot, then you can create a mold and have a silicon part that is the deformable part. You put the magnet in, and then it's job done, at least for this relatively simple version of the sensor. One advantage, as I said, is that these are easily miniaturized, so you can then use flexible electronics and put several sensors together, and this is work in collaboration with Waseda University. in Japan, and you see now we are doing a similar thing as in the previous video, but with more sensor, we can be more accurate in detecting the force because we have a better appreciation of the area of contact. We detect slip, we can say something about the weight of the object, etc. Using the same technology, we are using here a flat version of this sensor that can be mounted on a gripper. And with this, we did some data collection that I call in the wild, meaning that there is no specific procedure, but it's just the robot grasping objects several times. And we collected data and we trained classifier that will then used in order to detect slip. And you can see here in the visualization of the sensor that for each tactile, in this case, we have 3x6 matrix of tactile. For each tactile, we have an estimation of the 3D force. And this sensor, by the way, are commercialized at the moment by Excel Robotics. You see the logo on the left. And we got quite good accuracy in the detection of slips based on our experiment. And I'll show you here a video just to give a possible application. This is one of the easiest things you can do with slip detection. You pick an object, then you detect that is slipping, you put it back down, and you do the grasp again. And the initial grasp in this case is based on vision. In this case, the grasp was better. We don't detect any slip, and so we can put it back. And you can see how important it is not to have the slip, not just for the object not to fall, but also to maintain the original orientation of the object within the gripper, so that when you position it back where you want to position it, you can do it precisely because you know what is the relative orientation of the object with respect to the gripper. And of course, this data can be used also for object recognition. And this is something we haven't done extensively yet, but just by looking at those tactile signatures of objects, and here you see some example of grasping the one object several times, or let's say grasping one object 2 times, you can see that the tactile signatures are similar for different grasps of the same object. And this means that even without, even in a kind of in the wild data collection, you might be able to get good data for to train classifiers and for object recognition. Second family of sensor is based on this cilia concept. So in this case, we have a soft cilia in which we embed ferromagnetic particles, and then we apply strong magnetic field to orient the particles all in the same direction, so that eventually we have a soft cilia, you see now in the video, that is magnetic. And then the concept is the same. We have a sensor down below that will detect the change in magnetic field. In this case, we are using either giant magnetic resistive sensor or tunnel magnetic resistive sensor, which are even more sensitive to the variations in the magnetic field. And now, because of the components we are using and because of the form of this sensor, this is now even more sensitive. And we use it, for example, for tactile scanning. Here we are moving this black robot that has this tiny cilia on top over a metallic sheet that had some apertures, some grooves. And we are able to precisely detect the position and the size of these apertures. And we do, in this case, we do it here with some relatively simple signal processing techniques. In another example, we apply a similar concept to trying to understand something about fruits. And here again, we do this tactile scan of the fruit. We collect some features from the signal, and then we use them to train classifier. And in particular, in this experiment, we show how we can be very accurate in classifying different types of fruits in whether they are ripe or senescent. And this is just a quick list of the papers that describe more in detail the 2 different technologies. And of course, you can ask me later if you want more detail about this. But so just to give now a kind of direction that I think it's interesting for considering the use of tactile for robotics. I think it could be interesting to have applications where we both handle challenging objects based on tactile, but also evaluate physical properties. And you can have an example of a robot picking a fruit, which is a delicate object, and we may want to know whether the fruit is at the right level of ripeness to be picked. Or we may have applications in challenging environments, for example, nuclear decommissioning, in which, in that picture on the right, the robot has to grasp a tube, like a connector, a hose, and on top of manipulating the item, we may want to see whether there are some defects, some imperfections in the tube, if the tube is broken. And that could be done ideally through tactile sensing, I think, complementary with vision, of course, but detecting some aspects of the physical interaction that are more complex to be detected by vision. And before concluding, I would like to mention also some work that we are doing in terms of, because we mentioned integration, and we are doing some work also in terms of software integration, because of course, when we then want to deploy robotic solutions that are a bit complex, it always involves the problem of integrating several software components that relate to different hardware that have to be integrated. And this is clear when we have application in which, for example, we want to combine vision and touch and the robot. At least you have 3 different things that you want to combine together, and it can be more. And so some work Brice, one PhD student in our team, has done in collaboration with Shadow Robot, is to create a software architecture that will simplify the definition and the deployment of robotic solutions. And this is based on ROS, but it then builds upon it, and it makes even easier for people, even people who are not trained in robotics, to deploy robotic tasks. And we do this with a combination of graphical user interfaces, and basically that will allow you to edit configuration files, and then this is automatically linked to a visual graphical user interface that will allow to build a task. And you can see some example here. And on top of that, the same interface can then be used to monitor the execution of a task. And what's interesting here is that we made a user study of this framework with several people with different level of background in programming and in the robotics. They try to use the system. And for those who have already some experience in robotics and in ROS, basically the advantage is that they can create tasks much faster, like considerably faster. For those who don't have experience, for example, in ROS, or don't have even experience in robotics, but have at least some experience in programming, it makes it actually possible to deploy robotic tasks. And the first one I showed, it's relatively simple from the point of view of the task. This one is much more complex, and you see here integration of vision, for example, and also some decision within the task. So for example, here the robot will pick the object and put it in the box, and then you will see next, it might miss one pick, and therefore deciding that he has to pick again. And you can see in the graphical user interface how the task can be monitored. And this is, of course, very important, because if something goes wrong, you may be able to pinpoint easily where the problems are and what needs to be updated. And with this, just give a short summary. I have presented some of the solutions for tactile sensing we have worked on, and explained some of the problems we have tackled, and some what I think can be interesting direction and applications for this. And then I quickly presented the software framework that we have been recently worked on. And that's me. Thank you for the attention, and I'm happy to answer any questions.
Okay, great. Thank you, Lorenzo, for the great talk. So we can go for questions now. Anyone would like to go the first? Otherwise, I will go first. Okay, and maybe people are just typing. I can ask my question first. So you have shown this grasping example, and you have put one camera as the arm, and the camera is viewing the object on the table. So my question is, as the camera is moving with the robot, so how do you tackle this problem, as you may have this shaking in the visual input?
Yes. So what experiment are you referring to?
So in your practice,
you mean the tactile, the slip detection?
No. Yes, that one. Yeah.
So yeah, so I'm not sure if I got your question exactly, but basically what we have in that experiment, we have an initial estimation of where the object is and the pose of the object, and based from vision.
Mm-hmm.
In the video, you will not see the image coming from that camera.
Oh, okay.
So the image that I was showing, the small image, it was just for illustrative purpose to zoom on the object.
Okay.
So we have a fixed camera in the environment from which we take typically RGBD information about the object. We plan the motion, we go there with the gripper, we lift the gripper, and then we detect the slip with the tactile sensors.
I see. Yeah. So you have the camera fixed at one point.
Yeah.
And okay,
so in that example, we had the camera fixed. The very last experiment that I showed, or let's say the grasping task that I showed, the very last, in that case, we have a wrist-mounted RGBD camera.
Yeah, great. I can see Professor Bilal has raised her hand.
Yes, thank you, Shan. Lorenzo, thanks a lot for the talk. I was very interested to know more about how you managed to learn about the property of the object once you have it in hand. You mentioned correctly that it's very interesting to learn it once you have it in the hand. And of course, the trade-off is you better learn fast, otherwise it's going to drop. So if you could give more information on this.
Yeah, no, indeed. And actually, we are always inspired by your work. And I think ideally there could be interesting way, at least theoretically, to combine previous learning that you do that can be used as priors, and then to improve that with observations online. I think that will be very interesting. Is not what we are doing at the moment. We are doing only the online real-time part. So basically what we do, we have the object in the hand. We do small movement of the fingers. For example, this small sliding that will help us to understand the local geometry of the object. And so that will help us to understand, so the assumption is that we don't know anything about the shape of the object. So we start from a grasp, and so that we know that we have fingers in a certain point, but we don't know what's the local geometry. So we don't actually know if the force we are applying. We start by applying forces directed toward the center, so toward the barycenter of the finger. But that might not be the best one, depending on the local geometry of the object. So we do a small exploration to understand the local geometry of the object. And at the same time, while we do that, we try to estimate the friction as well, so that we have an idea of the friction cone. Once we have that information, then we do some optimization to reduce the net force, but we do it within the boundaries given by the estimated friction cone that we have found.
Okay, that's very interesting, because then you have to decouple the fingers, right? So you have to choose which one you can slide and by how much. So do you first apply a little bit of rotation to determine the friction cone, and based on that you can then decide which finger to move?
We typically do a kind of inward movement of these two fingers. We assume that we have a kind of grasp in which we have the thumb on one side and the three fingers on the other side. So that's, I would say, an assumption that we make. We do a little inward movement of the external fingers. And that's what we use for the to get estimation of the local geometry. And then we do this, as you mentioned, a little rotation, which is not, it's just a tiny rotation. We actually control the force applied by the finger. So just a tiny rotation will change the force that we are actually applying on the object. And we do the exploration in that sense. And then I forgot to mention, we stop this exploration when we detect a slip. And which is by itself also challenging, because in this case we are using this optoforce sensors. This is a 3D force sensor. We can have an estimation of the slip by looking at the frequency, by looking at the power spectrum of the force signal, which is a technique used in the literature that has some limitation, I would say.
Thanks, Lauren.
Okay, I think we can have a break now, but Lorenzo, please, I have seen there's some other questions in the chat box. You can answer there. Okay. So as I mentioned before, we have